And we're going to be talking about the red planet, which is, of course, Mars. I hope you realise that. It's the fourth planet out from the Sun, and it's one of the four rocky planets of our solar system. And in many ways, as you'll discover, it quite resembles the Earth. And because of that, and also the fact that it's our most accessible planet, it's the one that comes nearest to us, it's the planet that I feel has really kind of captured a lot of the human imagination through the centuries. And not just that, it also means it's a very easy focus for our space exploration. And there are many ways in which we know an awful lot about the surface of the planet Mars. So it's a terrestrial planet, it's the fourth out from the Sun, so it's the next one out from the Earth, which means it's a colder planet because it's that much further away from the warmth and the heat of the Sun. And it's about half the size of Earth, just to scale here, which means it's still bigger than the Moon and Mercury. But packed within that volume, it's only got about a tenth the Earth's mass. So the gravity on Mars is a lot weaker. It's about a third of that of the Earth. So when you look at Mars with the unaided eye, it just looks like a star. You can see that distinct red colour, obviously it's what lends its name to it being the red planet, but you need a telescope to resolve it into a disk. And despite that, it wasn't until like 50 years after Galileo first turned a telescope to the heavens that people actually began to see features on the surface of the disk. So in 1659, Christian Huygens, Dutch astronomer, first noticed an irregular kind of blotch mark on the disk of Saturn. Now, he'd looked 3 years earlier, and he'd looked at the planet 3 years earlier, and he'd not seen any features on it, completely blank. This time, it was a slightly closer apparition of Mars. It was closer to the Earth in its orbit around the Sun, and he saw for the first time this dark blotch. We now know this as a feature we call Syrtis Major. It's an irregular patch that he's kind of tried to sketch in this drawing. And just by watching how that patch rotated into and then out of view over the next few days and weeks, he calculated that the day on Mars was just slightly longer than the one on Earth. This was confirmed a little bit later, a few years later, by Domenico Cassini, the Italian astronomer, who also followed these features on the surface of Mars and confirmed Huygens' result that the day on Mars is only 37 minutes longer than that one on Earth. So that's the first similarity. Day length is very similar. And both Huygens, in later observations, and you can see in Cassini's drawings, notice the white caps at each end of Mars. 100 years later, the English astronomer William Herschel showed and demonstrated that the tilt of the rotational axis of Mars, again, is very similar to the Earth. It's 25 degrees, so just slightly larger. And this is an important point, because if you have a similar tilt, that means that you get seasons. You get the same seasonal changes on Mars than you do on Earth. So it goes through all the same seasons, winter, summer, spring and autumn. The only catch, of course, is that they last twice as long, because it takes Mars 1.9 Earth years to go once around its orbit. Of course, it's not that similar to Earth in terms of its seasons. Not only do they last twice as long, but they're a lot more extreme. And there's a big disparity between the north and the southern hemispheres. And this is because Mars' orbit around the Sun is ever so slightly more squashed than that of the Earth. So if this is the Sun, and this is the orbit of the Earth and the orbit of Mars, not accurately to scale, of course, you find that when Mars is at perihelion, so that's the posh word for the point in its orbit closest to the Sun, it's at 207 million kilometres distance. When it's at aphelion, so at the other side of its orbit, furthest away from the Sun, it's a full 42 million kilometres further away. Now, when this is combined with that tilt in the axis, that means that the southern hemisphere, which experiences the summers when it's closest to the Sun and the winters when Mars is furthest from the Sun, has a greater seasonal variation. It has the most extreme summers, the hottest summers, the most extreme winters, the coldest winters compared to the northern hemisphere. So already there's quite a disparity in the seasonal change between the north and south hemisphere. This is also, this kind of squashiness of the orbit relative to the Earth tells you why sometimes Mars is easier to both observe and to get to at different times of the year, or its year. If you imagine the Earth is going around this orbit and Mars is going around this orbit, every so often they coincide, so the distance between them can be as low as 35 million miles. Other times you can obviously have the Earth on one side of the orbit and Mars on the other. So the best observations, so like when Huygens first saw that dark patch that was Syrtis Major, happened when they're close together. And also when they're close together, that's when the space agencies send a whole barrage of space missions off to Mars. There are some times when it's a lot more economic to send a spacecraft to another planet. And this schematic details 2003. Don't you remember, but that's when things like the Spirit and the Opportunity rovers were sent. The ill-fated Beagle lander. There was a whole flurry of activities, and so you get these bursts of missions to Mars when it's at this favourable point in its orbit relative to the Earth. Okay, Mars, unlike the Earth, has got two moons, and as you can see, those moons don't look anything like our moon. First of all, they're all irregular in shape. They're very small, they're very dark coloured, and for those reasons they weren't discovered till 1877, relatively late on in the study of Mars. And they're cratered, they're very small. This is the largest moon, it's called Phobos. Its longest dimension is less than 30 kilometres. It doesn't have enough gravity to pull it into a spherical shape. You've got craters, you've got marks all over the surface. And the other moon is called Deimos, which is substantially smaller. Now, the thing about Phobos, the larger moon, not only is it irregular, but both of these asteroids look an awful... Sorry, I've given the game away. Both of these moons look an awful lot like the asteroids in the asteroid belt. And in fact, we think they were stolen from the asteroid belt by Mars. Maybe they've just been nudged closer to it by the gravity of Mars and gravity of Jupiter, but they've been pulled into orbit and they're now captured asteroids, which have become the moons of Mars. Now, Phobos, this one that's spinning steadily here, is very close to the surface. It only orbits about 6,000 kilometres above the surface of the planet, and that's above the equator. That means if you're at the poles, you can't actually see Phobos. And if you're on the equator, you see it rise and set 3 times every day because its orbital period is 7 hours 39 minutes. So it's kind of whizzing round the planet. Here's a very nice, it's not really an eclipse, but a set of Phobos moving in front of the sun as seen from one of the landers currently on Mars. So it's very close to the surface, which is not good news for Phobos. Its orbit is shrinking at a rate of about 1.8 metres per century. It's not going to stay in orbit around Mars for an awful lot longer. Well, astronomical terms, probably in about 500 million years, which is, not long in the lifetime of our solar system. It'll either be shattered into bits, by the tidal gravitational forces of Mars. Maybe that will create a temporary ring around the planet, or it could even crash onto the planet's surface. So it's not going to be a long-lived moon. The other little moon, Deimos, which you can just see one moon eclipse and the other, is a lot further away, and it's probably about as far away as you can get from the surface of Mars and still be retained by its gravity. Mars has been the subject of its own space race. We're all familiar with the idea of the space race between Russia and America to get to the moon. There was a parallel space race to send missions to Mars. And even though the Russians were the first ones to launch a spacecraft to Mars, Mars 1, unfortunately communication with that ceased. And it wasn't until the Mariner program, a little bit later from the Americans, that we began to learn more about the planet. Mariner 4 did the first fly past of the planet. It went within about 9,500 kilometres of the surface and took 22 photographs. And this was later followed by Mariner 6 and 7, which did closer flypasts and sent back about 200 photographs of the surface, and then Mariner 9, which was sent into orbit around the planet. And all of these revealed there's a wealth of features on the surface that you cannot observe from Earth. You've got craters. I'll show you some of these things. You've got craters, you've got volcanoes, you've got a huge canyon. All of these that were hitherto unknown. The first lander the first spacecraft to actually land on Mars was again a Russian one, Mars 3, I think in the early 70s. which had the misfortune to land on Mars in the middle of a huge dust storm. And so communication was again rapidly lost from it. So again, the first successful landers didn't happen until a few years later, in 1976. The Viking landers, which I'm sure we all remember, incredibly successful missions. And they were monitoring the composition of the atmosphere, the weather in the sky, the property, the chemical and mineralogical properties of the soil, monitoring seismic activity. And you can see in this lower picture, they even had a scoop which would scoop down into the soil. And one of the things they were looking for was to test whether any organic compounds in the surface layers of the soil, a test which proved unsuccessful. And so that meant that certainly life on Mars, if it is there, wasn't going to be easy to find, and it wasn't sitting on the surface just waiting for us to discover it. Of course, now we have moved to a completely new phase of Martian exploration. There's a whole host of new rovers on the surface and orbiters mapping it from the sky. This, for example, is a drawing of the Spirit and Opportunity rovers. They landed on the surface of Mars in 2004 and have returned a huge amount of information. We have also had several satellites, such as the Global Surveyor or Mars Express, and most recently the Mars Reconnaissance Orbiter, which are mapping the surface of Mars in fabulous detail, resolving structures only a few meters across. So you can set beautiful kind of rippling sand dunes and really understanding the geology of Mars from these orbiters. This is what it would be like if you stood on the surface of Mars. And you could fool yourself, you were somewhere in an Sahara Desert or some sandy desert somewhere. There are a lot of differences in Mars. I've told you already the gravity would be a lot weaker. That would be the first thing you feel. But one of the main differences is one that is not apparent from any of the images I'm going to show you. And that is that Mars does not have a global magnetic field like the Earth. We think it used to. The oldest rock on the surface of the planet shows some residual magnetism, suggesting that Mars once had a strong magnetic field about 4 billion years ago. But more recent terrain on the planet does not have any of this residual magnetism. So about 3.9 billion years ago, Mars lost its magnetic field. We don't know how. It could be a particularly heavy bombardment or impact during that time when there was a lot of debris left over and the planets were still forming in the early solar system. Maybe that disrupted the core and removed the magnetic field. But this lack of magnetic field leaves Mars very vulnerable. First of all, you are fully exposed on the surface of Mars to all the dangerous radiation that comes from the sun, in terms of what we call the solar wind, this stream of charged particles that bombards the surface. Not only is the surface vulnerable, but so is the atmosphere. Mars has an atmosphere. It's had volcanoes in the past. We think it had a lot thicker atmosphere in the past. But as soon as the magnetic field was stripped away, it leaves the outer layers of the atmosphere very vulnerable to themselves being stripped away. Remember, they're not so strongly tied to Mars because of the weaker gravity. And the solar wind and radiation has blasted the atmosphere and stripped a lot of it away until what is left is a very tenuous, very thin, sparse atmosphere. This atmospheric pressure is about 1% of that on Earth, so it's more or less a vacuum on the surface of Mars. Not just that, but the atmosphere is poisonous, or would be poisonous to us. It's mainly carbon dioxide with a bit of nitrogen and a tiny bit of argon and maybe a slight smattering of oxygen and carbon monoxide. You're not going to have an ozone layer because you don't have enough oxygen. So again, that doesn't protect you from the harsh UV radiation from the sun, and that affects the chemistry of the soil. So it's a very thin, very tenuous, quite poisonous atmosphere, mainly carbon dioxide. So this atmosphere means that you don't get meteorites burning up so readily as you do on Earth, so you get a lot more impacts on the surface of Mars as well. Now, between the atmosphere and also the temperature on Mars, okay, it's cold on Mars. It was quite nice outside in London this morning, wasn't it? Yeah. You'll probably get to that temperature on a midsummer's day on the equator at midday on Mars. That would be your very best bet. most of Mars is going to be around minus 60 degrees C. At the poles, you're going to drop down to minus 150 degrees C. Okay, so you can immediately see one problem is that the carbon dioxide will fall out of the atmosphere. You'll actually get precipitation. The atmosphere will freeze during especially those extreme southern winters. And if you're removing carbon dioxide from the air as snowfall, that means you get huge variations in the air pressure. So it's weak to begin with, and then you get seasonal variations as up to a third of the carbon dioxide in the atmosphere kind of condenses out as snowfall during the winters. So you get huge variations in this pressure, and these cold temperatures and this absence of any real air pressure means there is no liquid water on the surface of Mars now. Any liquid water in any quantity, it's either going to freeze or sublimate away. It's this combination of the lack of atmosphere and the cold temperatures that does for it. Now, the surface of Mars is red because it's rusty. There's a lot of iron in that surface soil. It gets oxidized to give that characteristic red colour. It's very dry. There isn't a lot of water. And so the surface of Mars is covered with a very fine dust, kind of desert grains and even finer particles. There's also a lot of weather on Mars. There's a lot of wind. I've told you there are these huge temperature changes. There are also huge pressure changes. And especially at the turn of the seasons, these differences in pressure can drive enormous winds across the surface of the planet. Winds of up to 200 kilometres an hour. And this can redistribute this dust and it carries it around the planet. First of all, you will see, perhaps in a photo like this, that the sky in Mars is pink. It's not blue. That's because a lot of these dry dust grains get carried up into the atmosphere and are suspended there in the air, and they colour the sky pink. And this has complications because they can absorb the sunlight and heat up the atmosphere. You can begin to see why it's quite difficult to land something on the surface of Mars when the atmosphere is kind of growing, expanding according to how much dust there is, and you've got strong winds that pepper the surface. So the atmosphere of Mars is kind of variable quantity. So first of all, you get dust whisked into the air and hanging there all the time. And then these strong winds can also shape dust on the surface, the sand on the surface. There are clear pictures of large desert dunes and ripple structures that we can see changing from these winds. On a small scale, the dust gets whipped up in small tornadoes. Again, as the ground heats up and heats the air above it, you can get little sort of vortices of air that whip up dust with them to create what are known as dust devils. Here's one seen from orbit, from one of these orbiters. So you're looking down on it and its shadow here. And these can stretch up to a few kilometres above the ground. And some of the landers have even seen them scudding across the surface of Mars. So these don't last long, but they're pretty vicious. They scour the surface underneath them, and they remove any lightweight material, and behind them they leave dark tracks. So again, when you look from orbit, there are these fabulous patterns just etched all over the surface of Mars, and every time it's these dust devils that only last perhaps a few minutes, a very short time, but they just leave these huge whirling tracks behind them as they've lifted material and erased it from the surface. Those are the small scale dust storms. Mars does things on an even bigger scale. And particularly at the turn of the seasons, when you've got that change in atmospheric pressure, you can drive even bigger winds, and these whip up more material into the air. And then you start getting a feedback process of the more dust you have in the air, the more it absorbs the sunlight, warms up the air, more it drives this differential, strengthening the wind, whipping more stuff into the air, and you get a feedback process which results in global dust storms. They can obscure the whole surface of the planet at a time. They can last for weeks or months. They will only ever stop when you get so much material in the atmosphere that actually starts blocking the sunlight and the air begins to cool, and then it ceases. So here's the start of one. You can see just beginning. I'll just show you the effect of one of these global dust storms on Mars. So here we are, June the 10th, 2001, and then just about a month later, you can barely see any surface features. So remember those early astronomers trying to map out early surface features on Mars. If you get one of these dust storms, there's no chance, even in a close apparition of the planet, that you're going to be able to make out any of those features. And so these can just completely scour the surface. And remember, they're redistributing the sand and the material the whole time. There's a lot of weathering on Mars from the winds. The ice caps are they have two layers to them. I've told you that during the winters it gets so cold that the carbon dioxide condenses out a snowfall. And this supplements and builds up the ice cap. And so you get variations in the size of ice cap. Now this is the northern hemisphere in winter. In fact, there's a dust storm just beginning down here. This is what it looks like in summer. You can see that shape just perhaps embedded in there. I've tried to do them to the same scale. This is water ice. And then all of this is an extra layer of carbon dioxide which falls out of the atmosphere and just builds up that ice cap. It's even greater in the southern hemisphere again. You have a permanent layer of water ice which then is supplemented by a much larger temporary cap of that carbon dioxide. And so the size of the polar caps waxes and wanes with the seasons. And because you have this continual deposition and then thawing, and then you have the seasonal dust storms, one of the features that we can map from orbit are layering of deposits, where you have ice and then dust and then ice, and all this seasonal cycle leaves these layers of how far the ice has expanded or retreated each time. And Martian geologists can read this much like we read the width of tree rings, and they can tell us something about the seasonal variation of Mars over, the last few millions of years. And they can tell us about any long-term trends, any long-term variation in the weather of the seasons of Mars, perhaps due to a change in the axial tilt of the rotation, or the way that the orbit of Mars might change slightly around the Sun. So again, you can start to tell something about Martian weather history from these deposits. The inside of Mars, we think, is fairly similar to the Earth. There's been some differentiation, which means that metals have settled out. You've got a core, mainly iron core, that was molten originally, and then you've got a lot of silicate-rich crust and mantle overlaying that. There's a lot less iron at the core and a lot more in the surface than there is on Earth, and the core's a lot smaller. Because Mars is smaller, that core did not stay warm for as long. It cools down more quickly because it's got a small volume, it's a small volume and a large surface area. The surface of Mars has got craters all over it. They can sometimes be obscured by the storms or filled in by the storms, but some of them are very large. I'm quite partial to this one on the left. Can you see the smiley face? And this is also a nice bullseye. You've got a crater within a crater. I don't know quite how you managed to get two impacts so completely lined up. So all over the surface of Mars, you have craters. But there are other spectacular geological features. And indeed, even just the simple geology of Mars is a bit weird, because you have a huge difference between the south and the north. Now this is an elevation map, a topography map of Mars, unravelled. So you have the lower part here, these are the southern lands, and this is the north lands. And the first thing you can see, because red is higher and blue is lower, that the southern hemisphere is on average about 5 kilometres higher in elevation than the northern hemisphere. And the southern hemisphere is heavily cratered. It's the older terrain. And so it looks like something happened in the north which either recoated the surface, maybe there was a lopsided upwelling of magma that came out and lava recoated the surface, or maybe very early on in Mars's history something tore off, maybe a big impact with another protoplanet, tore off the crust in the northern hemisphere, leaving it to resurface itself. But this is called the crustal dichotomy, a big difference between the north and the southern hemisphere. And again, we don't quite understand the origin for that. It happened when Mars was, it was a few million years into its history. So perhaps about 3.8 billion years ago, or even slightly more recent. So if I just put that kind of onto globes, there we are. You can see the southern highlands again with lots of craters. These are all craters from, most of them from that very heavy bombardment that happened early on in the solar system, when there was a lot of debris left that was falling onto all the inner planets, providing the craters that we see on Mercury, on Mars, and on the Moon. There's one crater here that's 2,300 kilometres across. That's a very early, very massive impact, but a lot of them are much older. You can see it here filled with snow. This is the dark Syrtis Major feature that William Herschel observed, and Huygens. And in the north, well, just straddling this low north and this high south, there's a bulge. It's a strange part of the planet that sort of swells out about 10 kilometres above the surrounding thing, and it's about 5,000 kilometres across. And this underlies where there are volcanoes on the surface of Mars. You have this large bulge, and it seems like there's almost been, again, an upwelling of volcanic magma, which has not broken through the surface, just pushed the mantle out slightly. And the fact that it's associated with the position of these volcanoes on Mars suggests that could be the explanation. So you've got this kind of bulge on one side of Mars, which, again, we don't see on other planets near to us. The volcanoes themselves are large. You've got weaker gravity on Mars, so if you have a continual vent of magma coming up and sort of gradually accumulating a volcano, it can get an awful lot bigger and still support its own weight. These are what we call shield volcanoes. Where we see them on Earth, it's places like the Hawaiian Islands, and you have an upwelling of magma creating the volcano. Now on Earth, we've got tectonic plates that slip, and so you get a chain of islands. You don't have tectonic plates on the surface of Mars. The upwelling all happens continually in one place, and you build up these huge mountains. Now, this is the largest volcano on Mars. It's called Olympus Mons. You could fit the whole of Britain from one end to the other here. It's about 600 kilometres across, 25 kilometres above the surrounding terrain. So that's effectively 3 times higher than Mount Everest. These are massive volcanoes. Now, most of them, the largest ones are in that Tharsis Bulge region on the side of Mars. They're all dormant now. Mars is no longer volcanically active, but it clearly went through a period where there was volcanic material outgassing and the creation of these volcanoes. And perhaps connected with the creation of that bulge, there's an enormous fracture in the surface of Mars. It's called the Valles Marianas, and it's named after Mariner spacecraft because they effectively discovered it. It's over 4,000 kilometres long. It's a canyon. It's up to 8 kilometres deep. It wasn't created by water. It is literally a split along some kind of fracture or some kind of fault line in the crust, and it could be connected with this bulge on the side when it was created. So again, Mars has got this fantastic geology which seems a lot more extreme than what we have on Earth. Now, there is water on Mars. The underlying ice cap on both the north and the south poles is of water. There's a trace amount of water vapour in the air. Here you've got clouds hanging around just the summits of those volcanoes. So you do get water vapour clouds as well as carbon dioxide clouds in the air. And we do see water ice elsewhere on the planet. So here's a picture from Viking, where one morning in 1976-77, a frost just covered the surrounding rocks. Similarly, from orbit, we can see craters, and you can test, obviously, the reflective properties of this ice. This is a crater 35 kilometres across, and this is a giant puddle of water ice. If any of you are planning to go to Mars, that could be a very good place to land. Somewhere you can go get water for your cup of tea from. And there's also water ice frost around sort of shaded regions of this crater. So there are areas where if they're in shadow, it's particularly cold, you do get pockets of water ice. Now, we know that there's also regions where there was water on the surface of the planet. Now, this is just a map of Mars, a globe of Mars, taken by Mars Express, and it's just detailing all the sites they found evidence for mineral salts. Now, if you see, every one of those dots is where they have a detection of what they call hydrated salts. So these are things that require water, liquid water, to form. Usually have evaporation of water and it leaves behind these minerals. and they are all heavily concentrated to the south. All those kind of old highlands, and anywhere there's a depression in the old highlands, you find evidence for a kind of smattering of this mineral salt. So we know that there was once liquid water on the surface of Mars. It's left behind, it's evaporated away and left behind this material. So we know that something's changed from the past to today. Now obviously Mars has got colder, and another of the things we know is there's a lot of ice below the surface. Again, 2 different spacecraft have gone and looked at the surface of Mars with a neutron spectrometer and also with ground-penetrating radar. And they discover there are enormous reservoirs of ice beneath the soil. And this is true even at the equator, as at the poles. There are aquifers of frozen water ice below the surface. Now, we don't know how deep they go. The ground-penetrating radar only goes like a metre down. And it's possible these could be up to 1 kilometre or more deep within the soil. But there's clearly water ice locked in the soil of Mars. It's all frozen in there. Where it becomes apparent could be when you have a later meteoritic impact, such as these 2 craters here. I hope you'll agree, when you look at them, they kind of look a bit sludgy. There's, oh, that's clever, excuse me. You can see a kind of ring round here where material, it's more like you kind of dropped a pebble in a muddy sludge. Or here, again, a very sludgy kind of splatter where you get the sense there's water in the material that has melted during the impact and then refrozen, and these overlapping lobes around the crater. So we see indications where perhaps this frozen water, this frozen ice has melted and then refrozen, suggesting again you've got a lot of water ice locked beneath the surface layers of Mars. Kind of permafrost, if you like. And one of the key things about permafrost on Earth that we see near the poles is we see a sort of polygon pattern, and this has also been seen on Mars. This is the Phoenix lander that landed in the northern regions of Mars, near the polar regions, and this is a view it took of the terrain stretching away into the distance. And you can see it's cracked into what they call polygons as far as you can see. This is characteristic on Earth of permafrost regions, where you've got that water ice locked into the soil. And with the change in seasons, that ice thaws and then freezes, and the soil and the ground that it's locked into will then swell and expand and then contract. And that seasonal expansion and contraction breaks and fractures the ground into this characteristic pattern. We see it right next to the Phoenix lander in those northern polar regions. We also see it from space, looking down at the surface of Mars. So this is just a black and white picture showing you these kind of ridge polygons, and within them, polygons within polygons and different scales. Again, very indicative of all that water ice deep within the soil. The evidence for flowing water on Mars is also apparent mainly from the orbital images mapping the geological surfaces. When the Mars Global Surveyor orbited Mars, one of the most exciting things they saw, looking at the crests of a lot of these sand dunes and the rims of crater walls in a lot of detail, were gullies. You can see here, they look for all the world like some kind of flow has happened. These were originally touted as perhaps from melting of that water ice within the soil. It may still be due to some melting of carbon dioxide. And indeed, we saw these gullies being created over a period of 6 years. New, fresh deposits would occur within, in this case, it's a crater wall, suggesting material had perhaps trickled down. Now, most of these now are attributed to melting of carbon dioxide ice within the rim of the crater, or perhaps landslips, a little bit of seismic activity or meteoritic impact nearby, loosening material to scatter down the slope. There are a few of these gullies that we think could be due to melting of water ice. They tend to be in the parts of the craters that are shadowed for most of the time, and so you can get a build-up of water ice there, and maybe they only see the sun occasionally, and then you get a rapid flood. But that isn't the key. These gullies are not the key evidence for water on Mars. Instead, you're looking for features that resemble valley networks, drainage systems, again similar to what we see on Earth. And here's an example from one of the Viking orbiters. where you get tributaries braiding together and coming together to form deeper channels. And this is an example of such a structure that we feel is very clearly formed by water on the surface of Mars. Now, to develop a network like this, you need a continual and steady trickle of water almost. So this could be perhaps from melting of the groundwater ice, some kind of seepage from, some kind of gradual seepage, maybe at the bottom of a canyon, and feeding a temporary flow that spreads across the surface of the planet for a short while, creates these channels and eventually dies away. There are channels like this on the surface that are due to water, and then there are much more dramatic events we think that have happened in this sort of continual steady seepage. So for example, here is a patch of Mars. It's a large valley where we see evidence of a much more torrential flood of water across the surface. And these are seen in various patches all over Mars. And if you look, you see the scale, 70 kilometres. So the width of these features, they can be tens of kilometres wide, they can last thousands of kilometres long. And if you look in detail at the structures within these large outflow channels, you can see streamlined structures. So here, wherever there's been a crater or something, it's like water has flowed around it and piled up sediment to form this kind of, this teardrop shape, this very streamlined effect. There's some there, there's some up here. And all of this shows perhaps a torrential flood, a very temporary flood of a lot of water. Again, just from the geology and other structures within these outflow channels. And the question is, where does this water go and where does it come from? Now, so where it goes, we think once you've initiated a sudden torrent of water, it'll flow very rapidly until it reaches some kind of low-lying basin, maybe a crater. It'll flood the crater and create a temporary lake or sea. Now, those are the lakes or seas that evaporate away and leave behind the mineral salts that we see from orbit. How it's created probably goes back to that subsurface ice. Some of these flows, here's an example, you can see a big flow channel stretching away down here, seem to originate in cracked, fractured land. There's another example in false colours here. It's an elevation map where again you've got a very clear flow that goes on and marries up with the one I was showing you earlier, but again it originates in very sort of cracked and fractured land. And the origin we think is again from subsurface water layers, where perhaps the weight of the overlying material presses down, heats the ice, and suddenly there's a huge collapse when it melts. The top layers crash down and the ice itself melts and creates this temporary torrent, this flooding across the landscape, which lasts for a while, creates these ancient lakes and seas, which then either sublimate away, evaporate away, or sink down and become again part of the frozen ice, the permafrost in the soil. So you get this cycle, which was mainly early on in the history of the Mars, could still potentially happen today. We see no evidence of it being very recent, and I'll come back to that. But certainly there was liquid water flowing across the surface of Mars. So there's evidence from orbit by looking at these geological structures, comparing them to what we know of water flow on Earth. But of course we have the luxury of exploring the surface of Mars remotely through our little remote control spacecraft. So in 2004, two rovers, Spirit and Opportunity, were landed by NASA on opposite sides of the planet, sort of fairly near the equator. And in both cases, they chose locations that we knew from orbital mapping, there was likely to have been water on the surface. So the first one, Spirit, landed in this crater. Look at the crater. You can immediately see it's indicative of a water channel that then filled this crater. Again, orbital mapping suggested that there's a strong preponderance of those hydrated minerals within that basin. Spirit has explored a good fraction of this basin. It landed over here. It went and had a look at this crater over here. There's the view of that crater from the vantage point of the rover. And then it crawled across here, and it went up into Husband Hills and down here, down to Columbia Hills. And this is a view from the hills. There's the flat basin of the crater in the distance. and you're up in these hills. And you can see the tracks of the rover here. Now, as it did that, it was examining the soil. Again, it confirms by doing an analysis. It's got that scoopy arm. It can analyse what's in the soil. It can, even its wheels turning over the soil, exposed. You can't really see it. There's a little bit smattering of white chemicals here. Again, these salts. It confirmed the presence that this looked like it was an ancient waterbed, that there had been water on this side of Mars. To the other side of Mars, Opportunity was landed in another region which, from orbit, they detected high levels of a mineral called hematite. Now, this is something that requires, it takes a long while to form, and it forms from, again, in a body of standing water. Very slow evaporation process. And this is a view from the Opportunity rover, a kind of pavement stretching away of rock, and scattered all over the surface, little bubbles. And when you look at them in detail, these are blueberries, what they call them blueberries. And again, with microscopic imaging, you can see them in more detail. All of these are little hematite granules. And again, they suggest they're a standing body of water that evaporated slowly away. So both sides of the planet, evidence, different kinds of evidence for liquid water. And not just any liquid water. I should stress it would be something that would be very acidic, very salty, not actually very nice water compared to the stuff we're used to on Earth. There's more evidence from other landers. Phoenix, as I said, landed in the northern polar regions of Mars. It didn't move, it didn't rove around the surface, it just explored its immediate environment in great detail. But again, it had a scoop, and this scoop could dig trenches down to about 15 centimetres down into the first layer of soil. And here's one of the the trenches it dug. This is the first image of it. You can see white material here, and I hope you can see there are some white blobs there. 3 days later, it looks like this. Okay? Spot the difference. These cubes down here disappear in some of this. The rapidity with which this is sublimating away shows it's water ice. So again, clear evidence for water ice within the surface of the soil. But not just that, Phoenix could do very detailed analysis of the soil. This scoop picked up surface layers and delivered it to the belly of the rover, sorry, not the rover, the lander. It not only did this microscopic imaging of the soil, it also baked it, sensed what was in the soil, and it detected the presence of a mineral salt called a perchlorate. And the key thing about this is that it is incredibly soluble. If you detect that, as Phoenix did, within the soil of Mars, it means there has not been liquid water for millions of years over that patch of Mars. So the fact this perchlorate is sitting there, if there'd been any water around recently, it would have all been washed away. The fact is there means that Mars has been dry for a long time. So the presence of this perchlorate has also been confirmed by our latest rover, Curiosity. Here it is on the lab on Earth, a NASA mission. It's about the size of a large mini car. You can see it's got a camera here. It's also got scoops, it's got lasers, it's got drills. It can do a lot of remote exploration and testing of the surface of Mars for us. It landed last summer in August 2012, and since then it's driven just short of 3 kilometres over the surface of Mars, and it sent back tens of thousands of images. So we really are looking at things on Mars in great detail. And like both the Spirit and Opportunity and the Phoenix, it has the potential to investigate both at microscopic levels, but also the chemical makeup of the soil, and just examine curious features it sees. Now, it's landed in a crater. Oh, this is just a selfie it's taken. Okay. It's landed in Gresham crater. Here's a kind of 3D relief picture from some of the orbital imaging. There's the crater wall here. The rover's about there, and you've got the central peak of the crater. Now, looking at that image, when you look at this selfie, you can see the crater wall in the distance here, and you can see the beginning of the central mountain, Mount Sharp, at the core of the crater. Now, again, you land your spacecraft where you think there's going to be something interesting to look at. Now, Curiosity is not looking for life on Mars. None of the current rovers and planned missions are doing that. What they're looking for are the kind of trying to piece together the water history of Mars. When was Mars warmer? When was it wetter? Is there true evidence for water, liquid water flowing across the surface of Mars? And in fact, it's already solved that very near where it landed. Well, okay, just to say about why it's landed in this crater is that again, you've got from orbit the idea that you've got these mineral salts within the crater, and there's also a cut in the crater rim which suggests that water flow is just kind of flooded, perhaps one of those surges has flooded over the rim and filled the crater sometime in the past. So right near the landing site, the Curiosity noticed some eroded rocks. So you can see layers of rock here, and if we just zoom in on this little nearer region and then zoom in on perhaps some of these outcrops, looking at that and examining it in great detail already provides evidence for liquid water on Mars. So here's a picture of this region now really close, and this is a similar region on Earth. This kind of, we call it conglomerate, is when you've got gravel, small pebbles, and it's all cemented together by finer sand. Where we see that on Earth is on riverbeds and dry riverbeds. When you look at the conglomerate on Mars and these outcrops, first thing you notice is that it looks like river gravel. The pebbles are too large to have been transported there by the wind. They're rounded, so they've experienced erosion, and they're all different colours, which suggests they've come from a variety of sites, being brought together by one mechanism, presumably liquid flow. And indeed, comparison to rivers on Earth and river deposits on Earth, the scientists suggest that they could have been delivered there within a liquid flow that's not travelling awfully fast and isn't particularly deep, probably somewhere between ankle and waist height. You've got a fair stream just eroding and depositing material and perhaps carrying it up to 10 to 15 kilometres away from source. And this fits with the idea that this crater was once flooded. Curiosity is there. There's the cut in the rim. And indeed, when you look at it in detail, the structures, is the idea of some kind of material that just spills over in a liquid flow and fans out over the surface of the crater. So it's already found that there are lots of evidence for there being flowing water on the Mars. But remember, a long time ago, because it doesn't find the percolates within the soil. Now, Curiosity is going to explore Mars for a while yet. It's now moving towards its main target, which is that central mountain. And this, again, is one of the key reasons for going to this particular crater, is the mountain at the centre. It is surrounded by sediments. You can see some of the deposits down here. If I zoom in on this region on a slightly enhanced picture, you can see there's a sort of difference between, on this picture they've just drawn dots to delineate the boundary between different kinds of sedimentary layers within the rock. Not just that, but if you zoom in even further, you can see sculptured sediment, and here ideas of more erosive activity and more deposition. It looks like there's an interesting water history there to examine, and that is where Curiosity is headed. It can't take a direct route. There are big kind of sand dunes within the way. It's going to have to take a circuitous route, and it's also going to get distracted. There'll be interesting rocks or outcrops that it'll go and look at in detail. But it's clear it's going to be turning up fantastic images and more detail from the surface of Mars for a while to come. And I'm sure we're going to see it in our news headlines. It's already showing that Mars has a complex and interesting water history. So the key thing is, why was Mars much warmer and wetter in the past, and now it's not? By the way, this is an artist's impression, we haven't really discovered. Liquid water on Mars. It's trying to give an impression of what it might have been like in the past. Now, Mars was obviously warmer. It had volcanic activity, but that cooled out a lot more quickly than it did on Earth. But the volcanoes will have delivered material to form a nice thick atmosphere. If you have a thick atmosphere, you have a greenhouse effect. You might have a warmer surface of the planet. The whole planet could have been a lot warmer in the past. The thing that we think is important is the removal of the magnetic field. Whatever did that, sort of 3.9, 4 billion years ago, that then changed the whole nature of the atmosphere. It was then free to evaporate away and get stripped off into space, and at that point Mars began to cool down and it began to become a very different planet. And that's probably the key factor in whether or not it now has liquid water on the surface. It's what impact or what event stripped away the magnetic field and then left the atmosphere vulnerable to exposure. Of course, if Mars was once warmer and wetter in the past, it could harbour life. Now, Mars is the one planet that springs to mind when anybody talks about aliens. You think about Martians. I'm afraid I'm not going to announce any great discovery. I'm not going to counteract the idea that there's intelligence on Mars. But a lot of this human fascination came from when astronomers, so this is the notebook of Schiaparelli from 1877, who, when he was observing Mars with his telescope, he could see dark structures. And he termed these canali, which is the Italian for channels, but it kind of got misrepresented when translated to the English as canals. And some astronomers let their imagination run away with themselves and suggesting this was an artificial origin. I mean, here's a map of Schiaparelli mapping out these structures on the surface of Mars. Now, he wasn't stupid, he was doing really good observations. And in fact, when you compare some of the drawings made by people like Lowell around the turn of the century to perhaps modern pictures of Mars, perhaps you just kind of squint and blur your eyes, you can see that they are you imagine through not a great telescope, you are representing what you see. Now, already by 1910, telescopic images and observations had ruled out these dark linear structures being real. Okay, they're more an optical illusion where the eye kind of if you have dark blotches, it kind of draws a line between them. It's a bit of an optical illusion. But it raised the idea, I mean, there were whole flights of fancy where these were canals bringing water to irrigate the desert from the polar regions and the dark, that you would see changes in the canals, which they attributed to seasonal growth, but we know is probably more likely due to the dust storms that would kind of obscured features or recoat features. So again, it was embedded in the human imagination, this idea of Martians. We now know, of course, it's not true, certainly not farming Martians. We haven't found any on the surface of the planet. But you still can't rule out that somewhere there could be microbes. If there is life on Mars, it would be what we term an extremophile. We get them on Earth. These are the bacteria that can grow in very acidic, very salty, very harsh, very cold conditions. Now, they will not exist in the surface layers of Mars because you've got no ozone layers. You've got harsh UV radiation from the sun. The whole surface is oxidized. You are not going to get anything surviving that environment for millions of years, from when it was warm and wet to the present of day. Now, where we think it could be, if there is life, it would be down deep underground. And after all, we have discovered extremophiles on Earth up to 1 kilometre below the surface. But it's going to be a while before we send a mission that does dig down into the surface that far and examine it. Ideally, what we want to do is to bring samples of Mars back to look at in the laboratory. Now, we haven't done that yet. Occasionally, Mars obligingly sends us samples. Remember, there's weaker gravity in Mars, and if you have a really big impact, some of the ejecta from that impact will fly off and escape the gravity of Mars. You only need to get to 5 kilometres per second to escape the gravity of Mars. And every so often, they'll go into orbit around Mars and then around the Sun and maybe intersect with the Earth and land as a meteorite on Earth. Now, there aren't that many of them, only about 20 Martian meteorites. We know they're from Mars from little bubbles of air in the rock that exactly match the composition of the Martian atmosphere, from the isotopic composition of the rock. In fact, I have a little bit of Mars here, by the way, delivered from one of these Martian meteorites. And you will remember in 1996 there was one particular meteorite where microscopic examination showed what was thought at the time to be like tiny nanofossils of early bacteria. The considered consensus now, a long time later, is that these are probably mineral structures, and even if they were fossils, you couldn't rule out contamination from Earth life. They're a lot smaller than any kind of Earth-formed life we expected. But nonetheless, it raised the idea from at that time that life could have travelled from Mars to Earth. Some of you may have read just recently in the last month, this has again been revived, with, again, analysis of the composition of the soil on Mars, and the idea that actually Mars could have been hospitable to life long before it was on Earth. Much earlier, it would have cooled down more rapidly. And there are certain elements in the soil, sort of chemicals of boron or molybdenum, that are in the soil on Mars in a good state these are crucial to how you make those molecular components for life, such as RNA, DNA, and proteins. And in fact, maybe they were in a much more favourable form on Mars and much earlier on Mars than they were on Earth, where they weren't necessarily in the right chemical form, in the right quantity, or they were dissolved in the oceans. So this has recently gone a resurgence that life might have started even earlier on Mars than on the Earth. But if we really want to test that, we don't have to rely on those meteorites that come from Mars. We want to go there. We want to bring back samples, and we are a long way off that yet. There are missions planned to Mars. They're going to carry on this mineralogical, this chemical, this physical analysis of the soil. It's going to be a long time before we start digging deep under the soil. And ideally, as I say, we want to bring samples back and bring them back to Earth. And that's considered really the next important step. You've got to prove you can bring things back from Mars before you can send astronauts there. It's not easy to bring things back from Mars, certainly people, because not only do you need all the fuel to get them to Mars and all their supplies to Mars, you then need to send all the fuel to Mars that you need to bring them back. And it's a kind of runaway effect. It becomes, very expensive, very unwieldy to do. Now, President Obama has challenged NASA to put astronauts on Mars in the 2030s, but over the summer you may have heard of other initiatives where they try and get around that issue of bringing people back. And there is one initiative, it's called Mars One, that's been in the news lately, where they're offering some successful candidates your chance for a one-way ticket to Mars. And you have to think about this as you are the first settler. It's not that different from early people settling Australia and the Americas. You don't know that you're ever going to see your homeland again. But the idea is, they've had over 200,000 applicants. Okay, so there are plenty. You don't have to be an astronaut to apply, and if you miss that round, there will be other rounds later. But they're looking to send the first crew of 4 people to Mars in 2023. Or launched in 2022, get to Mars in 2023. And there've got to be all kinds of missions to deliver stuff and scout out landing sites. But this is, quite an exciting possibility. That in fact, it could be a private company, it's a not-for-profit company, who are going to finance all this by selling the meteorites. Okay, so it's going to be Big Brother on Mars, right? Which of the astronauts get chosen, that first crew on Mars, is going to be by popular choice, popular involvement. And it's a completely different way of going about choosing your astronauts to Mars. I must admit, I haven't signed up. I think I know too much about the surface of Mars to know it's not a nice place. It's not just the atmosphere, the dangerous radiation from the sun, the cold, the lack of water. It's the weaker gravity would destroy bone and muscle mass. There's a lot of negative things about the surface of Mars. So I've not applied, but believe me, I will be cheering those astronauts all the way. Yeah, I'm very, very pleased somebody chooses to go, but I'll just sit on the sofa and watch. I certainly won't go for the first crew anyway. However, as I say, there will be further rounds. So if any of you are inspired by my lecture to go to the surface of Mars, you will get other opportunities to join subsequent crews for this colony on Mars. Okay, so thank you very much. I'll just end and tell you that in a month's time, I should be talking about quasars, a completely other end of the astronomical spectrum. Thank you.